Okay, so now that we've agreed on a rough cost model for the two operations all gather and reduce scatter, we can start to talk about the cost of performing dense matrix vector multiplication given different data distributions. So we're going to start by talking about a particular one-dimensional distribution of the matrix A and the vector x. And the conclusion we reach will be the same with the other data distributions, so we'll just stick with this one. Okay, so in particular, what we're going to do is take the matrix A and divide it into different sets of columns and give each of those sets of columns to a different process. So on the board, you see a matrix A that's been divided into 16 different sets of columns, which we might call A sub 0, A sub 1, etc., all the way up to A sub 15. Okay, and so equivalently, we've divided a vector x into 16 different sets of entries. So process 0 would get the first n over 16 entries, process 1 would get the next n over 16 entries, etc. So what's natural then is to express this product A times x as the sum over all the processes of A sub q times x sub q. And so what this implies is that if we had 16 different processes, we could have each of them locally perform their matrix vector multiplication with their portion of A times their corresponding portion of x. And then what they want to do is sum these results in some way and then perhaps distribute the result. Okay, so if you look at the dimensions of each of these submatrices of A, they're n by roughly n over 16. Okay, so what this implies is when you compute the local product A sub q times x sub q, this is going to produce a vector that's of length n. So what we then want to do is sum all of these different contributions to the final result and then scatter that final result between the processes. Right, so the main conclusion comes from when we think about what is the maximum number of processes that we can effectively use to perform this distributed matrix vector multiplication. So since we're dividing the columns of A amongst all the processes, naturally we can at most use P equal n number of processes. And so if we did so, we'd see that the sequential computation phase would require order of n work if P was equal to n. And then the communication phase would also require order of n work. So what we see is that no matter what we do, the runtime of this parallel algorithm will, at the very least, be order of n. So what we're going to do next is describe a better data distribution which can significantly lower the runtime of the algorithm if we use more processes.